Hello guys, welcome back to my channel. So in the last couple of videos, I had begun solving the ISC Math 2020 board exam paper. So we covered section A in two videos, and now it's time for section B. So the structure of this ISC Math exam is such that section A is compulsory, but you can choose from either section B or section C and do any one. So now I must confess that I hadn't ever touched section B throughout the entire final year of high school. Because I was planning to attempt section C in the final exam. But during this time, after having done some courses in linear algebra and multivariable calculus, I found I found it in myself to be able to tackle these problems. So let's get started, and my solutions may not be the up to the standard of what they expect in the ISC board exam, but I hope to give you some great insight in through my solutions. So don't worry, they're completely mathematically right. So no, I won't post like bad math content on a math channel, primarily math channel. So anyways, let's get started. Okay, so we had a total four questions in section B, and question 15 had you could choose between A and B. So let's do both. Let's do A first. It says write a vector of magnitude 18 units in the direction of the vector I cap minus 2 j cap minus 2 k cap. You can call this a hat or a cap. I don't care. It's just as long as you just don't say a regular I. So in the direction of this vector. So first of all, let's call that vector A. A vector, or A bar if you want, is equal to I cap minus 2 j cap minus 2 k cap. And now to find a direction of this, we need to normalize this and normalize it in such a way that, say, the normalized version of this is A cap is defined to be A vector divided by the magnitude of A vector. So we need to find the magnitude of A vector and divide this A vector by it. So magnitude of A vector is using the Pythagorean theorem in three dimensions. We have coefficient of I cap squared plus coefficient of j cap squared. So ignore the negatives, it will be 2 squared, and then coefficient of k cap squared. And that um, turns out to be, this will be 4 and 4, 8 plus 1, 9, square root of 9, which is 3. So the normalized A cap is A vector divided by magnitude of A vector, and that turns out to be 1 over 3 because the magnitude is 3 times I cap minus 2 j cap minus 2 k cap. Okay, but this is just the direction. This is just the direction because this is a unit vector, right? We normalize this. Normalization means uh, having a magnitude 1 for the resultant vector. So this is magnitude 1. So this only tells us about the direction of A vector. So we found out the direction of A vector. We got that. And a magnitude of 18. So the new vector, if you call it B vector, is defined as 18 because that's the magnitude times the direction A cap, because a vector is magnitude multiplied with the direction. So the direction as directed in the question has to be the direction of A vector, which we found out to be this A cap, and the magnitude has to be 18. All of this is given in the question. So 18 A cap. So we have 18 over 3 times I cap minus 2 j cap minus 2 k cap, which turns out to be 6 and multiply everything. 6 I cap minus 12 j cap minus 12 k cap. B vector, that's our required vector of magnitude 18 and in the same direction as a cap. A vector rather. So yeah, that's our answer. Okay, so moving on to subpart B of question number 15. And before doing that, I would just like to add that I made a mistake in describing question number 15. So question number 15 does not have a choice. It has A, B, and C, not just A and B. And there is no choice. All three of them are compulsory. Each of these three subparts is for 2 marks. So total question number 15 is 6 marks. Just that correction, nothing else. Anyways, so moving on to subpart B, it says find the angle between the two lines x plus 1 is equal to 2 is equal to y minus 2 is equal to 5 is equal to z plus 3 is equal to 4 and x minus 1 equals 5 is equal to y plus 2 over 2 is equal to z minus 1 over negative 5. Okay, fair enough. So let's look at this first. So we have x plus 1 over 2 is equal to y minus 2 over 5 is equal to z plus 3 over 4, and let that equal to some parameter t. So because then x will just be, all this is equal to t, so 2t minus 1. Y will be 5t plus 2. Z will be 4t minus 3. So our point, our line in terms of parameters is 2t minus 1 comma 5t plus 2 comma 4t minus 3. That's basically our line in terms of parameters or dynamic points. So as t varies, this point will move and trace out a line in three-dimensional space. And we can do this similar approach with this second line actually. So we have x minus 1 over 5 is equal to y plus 2 over 2 is equal to z minus 1 over negative 5. Let that equal to some other parameter, call it lambda. So x is 5 lambda plus 1, y is 2 lambda minus 2, z is negative 5 lambda plus 1. So our parameterized line in terms of dynamic points parameterized is 5 lambda plus 1, that's the x coordinate, 2 lambda minus 2 y coordinate, and negative 5 lambda plus 1 z coordinate. So dynamic point that traces out a line in three-dimensional space as lambda varies. So we have these two parameterizations. So if you remember our classic two-dimensional vectors, um, if you wanted to find the angle between two vectors, that's basically, in other words, saying angle between two lines, or you can say angle between two vectors. What you would do, say you had this p vector and a q vector, what you would do in two-dimensional vector algebra or linear algebra, whatever you want to call it, you would dot p with q and divide by the magnitude of p times the magnitude of q, and that by definition of this dot product would be cosine of theta, where theta was the angle between them. Okay, so I actually want to do a similar analogy for three-dimensional space. So we have this vector, you can see, because you can write this is 2t minus 1 I cap plus 5t plus 2 j cap plus 4t minus 3 k cap. So you can write this in terms of this vector like this. So you have a vector in three-dimensional space, and you can do the similar thing with this second parameterization. So cosine of an angle between these two lines, like we need to find, will be given by this 2t minus 1 comma 5t plus 2 comma 4t minus 3 dotted with phi lambda plus 1 comma 2 lambda minus 2 comma negative phi lambda plus 1 divided by the magnitude of this guy, the magnitude of say call this v1, multiplied with the magnitude of say this guy, which is called as v2 for example. Right, but the catch is we have to also deal with these parameterizations, right? We can't have an angle in terms of t times lambda and weird stuff. So I urge you to only look at this uh, number that's multiplied with t, that's actually multiplied with the parameters. So if you look at these numbers, 2, here we have 5, here we have 4, dotted with the same thing here, do the same thing, 5, comma 2, comma negative 5, okay, divided by say, the magnitude of this vector, which is 2 squared plus 5 squared plus 4 squared, times the magnitude of this guy, which is 5 squared plus 2 squared plus negative 5, forget the negative 5 squared for the magnitude. That would be cosine theta, the angle between, the cosine of the angle between them. Now, why did we only take the number multiplied with the parameter? That's because if you call this the x component, then this is like saying x is, you are shifting by 1 because of this negative 1. You're shifting uh, that location of x, of the x component by 1, while maintaining this inclination of 2 with respect to say the t axis, the parameter axis, the time axis if you want. So I mean, it's hard to draw this in three-dimensional space, representing that on a paper like that. If you call this the z-axis, I don't know, probably call this x, call this y. Then if you have some parameter axis, then this 2 is actually the slope of um, whatever curve you have with respect to um, this parameter axis in the x component of it. X component of this curve has a slope of 2 with respect to the x-axis. Yeah, I would like to put it that way. And slope of 5 with respect to y-axis, slope of 4 with respect to z-axis. So that's why, and these adding these numbers that you add, this -1, this +2, this -3, is how much are you shifted. So if you're like 1 is like here, 2 is like here, so how are you shifted from the origin? And you forget that, right? Because you are concerned with the angles, and it doesn't matter how far you're placed on the x-axis, how shifted you are on the y-axis or the z-axis. All that matters is this inclination, or this angle that it subtends with respect to that axis, which is in this case 2, 5 and 4, and 5, 2 and -5 for the second curve. And then likewise find the magnitude of those numbers, and that is actually an analog to this formula that we had for two-dimensional space. And these quantities 2, 5, 4 are what you call direction ratios or direction numbers. They are basically these denominators you had over here. So there was a direct formula. If you were, if you actually learned section B instead of section C, you would know this as the formula for the angle when direction numbers are given, direction ratios are given. But I just wanted to give you a more general picture of what is going on. So now calculating the cross product, we have 5 times 2, which is 10, plus 5 times 2, which is 10, minus 5 times 4, which is 20, divided by square root 45, square root 54. And because of this 20 minus 20, entire things become 0. So cosine theta is 0. And what elementary angle cosine of that angle is 0. So, well, theta will be pi over 2. So that is to say that these two lines in three-dimensional space are perpendicular to each other, believe it or not. And you can graph this up if you want. You can graph this with a 3D graphing calculator if you want, like GeoGebra or something, and you'll see that they indeed are perpendicular to each other. Okay, moving on to question 15, subpart C. They're telling us to find the equation of the plane passing through the point 2, negative 3, 1 and perpendicular to the line joining the points 4, 5, 0 and 1, negative 2, 4. So what we actually want to do is, what have they given us? They've given us a line that is perpendicular to the plane. So let's draw some plane, a required plane, and there is some line that's perpendicular to this plane. Okay, and this point of 2, negative 3, 1 actually lies on this plane. So probably you can say it's at this base of this vector like thing. So it's, actually when they say that they've given a line, we can actually interpret that as a vector. So they've given us the start point 4, 5, 0, and they've given us the end point, which is 1, negative 2 and 4. Fair enough. So say assume, there's this point in, say, free space, and then there's this point in free space. So if you were to represent this point as a vector 4i cap plus 5j cap plus 0k cap, it would be, if this is like the origin, this is like the origin O, it will be this vector if you want to represent it graphically by drawing like this. And then if you want to represent this point as a vector, it would be this vector. So to find a vector that joins 4, 5, 0 and 1, negative 2, 4, we would have to actually subtract 4, 5, 0 from 1, negative 2, 4. So the ending vector minus the starting vector to find this vector that actually joins them, which you can also interpret as a line that is joining the points. So instead of finding the equation of the line, let's find actually the vector. So call that A, the required vector, and as I said, end point. So 1 I cap minus 2 j cap. I'm writing this point in a vector form, this vector basically, plus 4k cap minus this vector 4 I cap plus 5j cap plus 0k cap, and that by doing just normal vector subtraction is negative 3 I cap, negative 7 j cap plus 4 k cap. So at this is vector A, because it's perpendicular, our plane is perpendicular to this line or this vector A, right? So if in the original picture this was the vector that was perpendicular to this plane that we had here, then let this be the representation of A, and this 2, negative 3, 1 can be considered to lie on this plane at the base of this vector. So how do we find the equation of the plane? So take any arbitrary point on this plane, call that x comma y comma z. Find a vector that is lying on this plane. So for that, this is your start point, this is your end point. You can find this vector by doing this similar method of end point minus start point. So call that vector B that lies on the plane. This dotted vector is B lying on the plane. So that is end point. So x minus 2 I cap, I'm doing it directly now, plus y plus 3 j cap plus z minus 1 k cap. And notice an interesting thing, since A is always perpendicular to this plane and B always lies on this plane, both of these A and B are perpendicular to each other. So A vector is actually perpendicular to B vector. And what do we mean by perpendicularity? It means A vector dot product B vector is equal to 0, right? Because the angle between them is 90, so the dot product will always be 0. So let's actually write, substitute now. A vector is negative 3 I cap, negative 7 j cap, plus 4 k cap, dotted with x minus 2 I cap plus y plus 3 j cap plus z minus 1 k cap. And all this is equal to 0 because their dot product is equal to 0. So simplifying stuff directly, we have negative 3 times x minus 2 minus 7 times y plus 3 plus 4 times z minus 1 is equal to 0. And if you can just simplify stuff, negative 3x plus 6 negative 7y negative 21 plus 4z minus 4. So we have this negative 25 plus 6 will make it negative 19. So that will go on that side. So we have 19 being equal to 4z minus 3x minus 7y, and that's actually the equation of the plane. Okay, finally moving on to question number 16. We have to prove now, and question number 16 legitimately had a choice between subpart A and subpart B. So you could do either. Let's do both. A first. We need to prove that A vector dotted with this quantity B vector plus C vector cross A vector plus 3B vector plus 4C vector is equal to the scalar triple product of A vector, B vector and C vector. So just to start, let's write our left hand side. It's equal to A vector dotted with B vector plus C vector cross A vector plus 3B vector plus 4C vector. Fair enough. Okay. So now what I'm going to do is I'm going to use the distributive property of uh, vector multiplication to distribute this term. So we have B vector cross this term. It's basically like a normal um, distribution of multiplication over, when you have one term is added, so one polynomial times another polynomial, you have to use the distributive property. It's basically that same thing, but we can't flip the orders because it's a cross product. So B vector cross A vector plus, because of this, B vector cross 3B vector plus B vector cross 4C vector. Okay, and then this plus C vector cross A vector plus 3C vector, or you can just say C vector cross 3B vector plus C vector cross 4C vector. And now one great thing that's going on is B vector cross 3B vector. You can pull the 3 outside because it's a scalar, will be 3 times B vector cross B vector, and any vector crossed with itself will be 1 because it will subtend an angle of 0 degrees and sine of 0 is 0. So this term will go to 0, and using the same argument even this term will go to 0. So we have two terms dropping out. We have A vector dotted now with uh, B vector cross A vector plus we can take the 4 outside. 4 b vector cross c vector, and we have plus c vector cross a vector plus 3 c vector cross b vector, like that. Now what I'm going to do is actually flip the order of this cross product. So we have a vector dot b vector cross a vector plus 4b vector cross c vector, and when I flip the order, when I make it from c vector cross b vector to b vector cross c vector, since the cross product is anti-commutative, we'll have a negative 3 b vector cross c vector plus c vector cross a vector. So these two cancel out nicely. So if a vector dotted with b vector dot a vector plus b vector dot c vector cross c vector, sorry if I said dot, plus c vector cross a vector. Okay, fair enough. Now what I'm going to do is I'm going to just rearrange these terms. So I have negative flipping the order of this a vector cross b vector, then again doing the same with this negative a vector cross c vector, and then keep this as it is, b vector cross c vector. And now I'm actually going to distribute this dot product over these subtraction and these addition. So a vector dot, take the negative outside, a vector cross b vector minus a vector dot a vector cross c vector plus a vector dot b vector cross c vector, and this is nothing but negative scalar triple product of a vector and b vector, and this is nothing but negative triple scalar product of a vector c vector, and this is scalar triple product of a vector b vector and c vector. But there's a property of scalar triple products. If two vectors in a scalar triple product are identical to each other, then the entire scalar product triple product goes to 0. So this will go to 0 and this will also go to 0, giving us a vector, b vector, c vector in a scalar triple product, just like we wanted over here. That's equal to RHS, hence proved. QED. And if you want an insight into why these two vectors in a scalar triple product make the entire scalar triple product 0, that's because you had this as your original definition of the scalar triple product. But the thing is, you can switch stuff as long as they're cyclical. So if A was at the start, B can take the place of A, and then these two A's move ahead. So B goes in the front. So this is nothing but B vector dot, this A moves ahead and this A moves ahead and this B goes behind, because they always have to be in a cyclic order. We'll have a vector cross a vector, same, any vector crossed with itself is 0. Same argument here, you move the C back behind. We'll have C vector dot a vector cross a vector being equal to 0. That's why these scalar triple products go to 0. Okay, so now we find ourselves doing question number 16, now subpart B, which was actually the option. So using vectors, find the area of the triangle whose vertices are A, 3, negative 1, 2, B, 1, negative 1, negative 3, and C, 4, negative 3, and 1. So instead of just directly jumping into the calculating the magnitude of the cross product, because determinant and stuff, let's actually construct vectors. These are just raw points given to us. Let's have a picture. Say A is somewhere over here, B is somewhere over here, and C is somewhere over here. So keeping B as our point of reference. We want a vector that originates from B and terminates at A. Call that vector P bar. And then we want another vector starting from B ending at C. Call that vector Q bar. And we can actually calculate what P bar and Q bar will be. So P bar will be the end point minus the start point. So basically A in vector form minus B in vector form, and that will turn out to be 2 I cap plus 0 j cap plus phi k cap. Same thing for Q bar also. C in vector form minus B in vector form. So you have 3 I cap minus 2 j cap plus 4 k cap. Okay, now so we have two vectors, and to find the area of the triangle that it will cover, we need to calculate the half of the magnitude of the cross product, because the magnitude of the cross product of P bar and Q bar will actually give the area of the parallelogram that they basically span, if you want to put it that way. But area of triangle is will be half of the area of that parallelogram, so half of the magnitude of P bar cross Q bar. And to find P bar cross Q bar, you do the matrix determinant method. So what you have is I cap, j cap, k cap, then first the P vector, 2, obeying the order. Again, the order doesn't matter here because anyways we want to find the magnitude. 2 0 5 3 negative 2 and 4. So what we're going to do is cover up this row and this column. We get 10 I cap minus and plus will eventually make it 7 j cap minus 4 k cap. You can do this calculation for yourself later. And now to find the magnitude of this cross product of P and Q, we just have 10 squared plus 7 squared plus 4 squared, which evaluates to square root of 165. And area of triangle, therefore the required triangle that we wanted to calculate, is half of this, right? Half of magnitude of P and Q, cross product of P and Q vector, which turns out to be half of square root of 165 square units. We again don't know what units were given. No units were given, so just write square units for area. Moving on to question number 17. Again, choice in subparts. So let's do subpart A first. Find the image of the point 3 negative 2 1 in the plane 3x minus y plus 4z is equal to 2. So the thing is, we have a plane. Whose equation is 3x minus y plus 4z is equal to 2. And they've given us some point which will not be located on the plane, otherwise this question literally has no meaning. 3 negative 2 1, say somewhere floating above the plane. So when they mean image of the point, they basically want to reflect this point about this plane. So the image of this point, which if you say call Q or P, will have an image Q, if you reflect it about the plane. So if you take this P to be like a small point light source and this plane to be a mirror, then the image of P, as you can see through the mirror, will be Q. Same distance from this, the distance that P was from this plane is the same distance that Q is from the plane. So equidistant, and we need to find the value of this, the coordinates of this Q. So now what I'm going to do is I'm going to, just play with this equation a little and find a point that is situated on the plane. So if I let x to be 1, y to be 1 and z to be 0, it will satisfy this equation because 3 minus 1 is equal to 2. So 110 is actually, say, some arbitrary point located on this plane. Say this is 1 comma 1 comma 0, some arbitrary point, okay? And what we're going to do, if you're going to let, assign another point, say if you call that xyz that lies on this plane, we're going to make a vector that is lying on the plane by doing the end minus beginning uh, formula. So we'll have x minus 1 I cap plus y minus 1 j cap plus zk cap. That's this vector that's always going to lie on this plane because xyz is always going to be a point on the plane. So to actually determine what the vector that's perpendicular to the plane is, we need to let that vector, call that, if you call this a, call that perpendicular vector to any point or all points on the plane, let that be x sub 1 I cap plus y sub 1 j cap plus z sub 1 k cap. So since I'm purposely going to make b pass through uh, p. So if you say call this, I don't know, let's have it in a downward direction, call this b vector. These will always be perpendicular. So like one of the previous questions, a bar dot b bar will be 0, and when you actually you know substitute and take the dot product, you end up with x sub 1 x plus y sub 1 y plus z sub 1 z is equal to x sub 1 plus y sub 1. And since this is supposed to give us the equation of the plane, this plane, we can compare it to this equation, 3x minus y plus 4z is equal to 2. So this means x sub 1 is 3, y sub 1 is equal to negative 1, and z sub 1 is equal to 4. So we have actually found a vector that is perpendicular to this plane. If you substitute everything in b bar or b vector, you get 3 I cap minus j cap plus 4 k cap. So what I did is I actually tried to reconstruct the expression from which we find the equation of the plane, and then compared it to the given equation of the plane because it's given, and then that helped us find a vector that is perpendicular to any point on the plane, vector that's perpendicular to the plane, as to say. And how that helps us is because now we can write a vector equation for this line PQ. So for line PQ, we can actually write a vector equation. So you can have a start point that's given to you. Say start point I'll write is 3 I cap minus 2 j cap plus k cap, and add t as the parameter because we are writing an equation for the line, times the direction, and the direction now is actually given by this perpendicular vector, right? Because we need this PQ, and this PQ has a direction of b vector. If you want to find the point Q, you'll have to go straight down perpendicularly into the plane and then emerge from this side. to reach Q. So you have to go perpendicular down. So we are using we're using the fact that B vector has always a direction that's perpendicular to this plane, and we're using that to use P as a start point and then write a general equation for this line PQ, and then plus T, that's the parameter for the line, times the direction of B vector, which is 3 I cap minus j cap plus 4 k cap. And you can call that, I don't know, equation for line PQ, or you can say PQ vector. This is like a parameterized vector, you can say, or a line. Line is a parameterized vector. And I would actually want to represent this using column matrices. So 3, negative 2, 1 plus T times 3 minus 1, 4 will actually give you 3 plus 3T, negative 2, negative T, 1 plus 4T. I'm just using these column matrices instead of vectors, just convenience. And now we need to find this point that is directly below P but on the plane. Call this M. So we need to let this parameterized line PQ solve the equation of the plane, because that's the only way we'll find M, because M lies at the intersection of line PQ and the plane. So we need to plug in, well, the equation of, well, this PQ in place of this XYZ in the equation of the plane. So equation of the plane was 3x minus y plus 4z is equal to 2. Instead of x, you plug in this value, right? Because that was associated with I cap, that is the x component, makes sense. So 3 times 3 plus 3t minus, plug in this for y, negative 2 negative t plus 4 times 1 plus 4t, and that is equal to 0. So we'll get a value for t. Stuff cancels out. T turns out to be negative 1/2. So the coordinates of M are now given by plugging the value of t in this matrix. 3 minus 3 over 2 is 3 over 2. This is negative 2 plus half, which will be negative 3 over 2 and negative 1. Those are the coordinates for M. So M can be represented as 3 by 2 comma negative 3 by 2 comma negative 1. That's this point M. Yeah. So now, but we know one thing, since this acts like a mirror, this plane acts like a mirror, M will be at the midpoint of P and Q, right? Because P will be a certain distance x, say x, or let's say d from M. Q will be the same distance d away from M because it's a reflection, right? So what we're going to do is use midpoint formula and calculate Q. So since M satisfies the midpoint formula, so x coordinate of M, 3 by 2, is equal to the x coordinate of P, which is 3, plus the x coordinate of Q, call it say Q sub x, divided by 2. Basic midpoint formula. Well, it seems I made a slight arithmetic error. This point is 3.5 or 7 by 2. Yeah, so just make those corrections everywhere. Sorry for this error. So yeah, then the 2's cancel and x coordinate of Q is 4. And we can do that for the y coordinate as well. So we'll have negative 7 by 2 being equal to negative 2 plus the y coordinate of Q over 2. And so the y coordinate of Q is negative 5, We can do that for z as well. So negative 1 is equal to 1 plus z over 2, implying q sub z. So q sub z is equal to negative 3. So q is now represented by, we know the x coordinate 4, we know the y coordinate negative 5, and the z coordinate negative 3. So this q just turns out to be 4, negative 5, and negative 3. That's the image that we want.